Um, Hello, welcome back to the continuing lecture in investments. This is Dr. Jeff Holm, and this is the video number 11 in risk and return. Now, so in our last video, we're basically, found the weighted average or the expected return under different scenarios, right? In other words, weighted average of return in of all four possible scenarios of the economy. So it was basically weighted average, but weighted by the probabilities of different instances or the scenarios of possible scenarios of the economy. So this is a in a way expected portfolio return because it's expected return because we are forecasting, trying to project potential possible states of the economy, and the portfolio return, which is a weighted average of all those under those potential scenarios, possible scenarios. And if it is past data, it's not expected, right? Past data is no longer expected, and past data, there's no possible scenarios because it's already past. There's only one scenario for the past. It's already done. Again, our question is, how likely are those scenarios? In other words, we used we assigned 5% probability for severe recession, 25% probability for mild recession, and so on. Of course, these probabilities are, as I said before, obtained by Monte Carlo simulation, which is basically a computer simulation of probabilities. But all those, basically think about it. All those, simulations come from is based on normal distribution, right? And we already know what normal distribution is from Finance 100. We already talked about this. Also, if you have taken Statistics 209, or you would already understand what normal distribution means. Of course, it's not only normal. There are many different types of distribution. First of all, there is uniform distribution. Uniform distribution is if there are four possible states of the economy, four possible scenarios, every scenario has the same probability. It would be the same same probability. It would be 1/4, 25, or 25%. Right? That's uniform distribution. Uniform, and then in another good example is rolling a dice. If you roll a dice, each number, and as long as the dice is a fair dice, fair cube, right? Meaning it's unbiased cube, right? A perfect cube has the same probability of 1/6 for every number, for every side on the cube, right? That's uniform. That will show uniform distribution. I mean, of course, when you roll a dice, multiple times, then the probabilities will change. But basically, if you roll a dice once, the probabilities are one. That goes without saying. But as you continue to roll a dice, multiple times in a row, theoretically, the probabilities would have to be the same, but the distribution won't be the same. I mean, even flipping a coin, right? And then there are binomial distribution. Binomial distribution is either, 1 or 0. I mean, there are two outcomes that can happen, right? So in binomial distribution, there is no central tendency. And then there is, chi-square distribution, which is, the distribution properties, which stems from the distribution properties of the squared, numbers. And then there is, Poisson distribution, and there's also log normal distribution, right? It's, log normal distribution is, of course, distribution of the logs, right? And so on. But most commonly, it's normal distribution, and normal distribution is something that happens in non-controlled experiments. In other words, in natural world, everything, most everything in natural world is normally distributed. And we understand the properties of normal distribution, right? The mean, represented by Greek character mu, right? And standard deviation, right? Represented by Greek character sigma, right? And we all know that within within one standard deviation, right? 68%. They sometimes, say this is not the right way to say it, but it's like 68% of the observations lie within one standard deviation around the mean. But that's not the right way to say it. It's the right way to say it is, if you have 100, if you have X number of observations, let's say it's 100, there's a 68% probability that the observation will fall within any observation of any observation would have 68% probability to fall within one standard deviation around the mean. Well, and then sometimes it is put or misinterpreted as if any random observation falls within 68%. Within one standard deviation, if it has 68% probability, doesn't that mean if you make 100 observations, then 68 of 100 observations will fall within one standard deviation? I mean, that's another way you can interpret it, but if you put it like that, it's like there's 68 will always fall. There's almost certainty that 68 will fall within one standard deviation around the mean, right? So that's why it is not the right way to say that. And the right way to say that is any random observation. If you pick any random data from pool of 100 observations, 100 data points, the probability of that random pick to fall within one standard deviation is 68%. Okay, and then oh no, oh no. What's going on? Okay, and then that means also there are then there is a 96%. Oh, come on. 96% probability. Yeah, the precise number is like 95.44%, but roughly about 96%. Okay, let's call it 96%. Probability that any random observation will fall within 2 standard deviations, 2 sigma. Okay, so if it is 96%, right, beyond beyond 2 standard deviation, right? They are called tail area. This is called upper tail, lower tail area, right? And then the probability of falling within falling in the outlying areas, right? Outlying areas would be a total of 4%, which means there is a 2% probability in the upper tail area. There is 2% probability of falling in the lower tail area, right? Now, so this lower tail, upper tail, right? They are called outliers, right? If you fall in this lower tail area, right? Like beyond, it's called outlier. Right? The outliers are, literally very rare, right? Extremely rare occurrence because I mean, if you are like a 7 foot tall, right, and if average height for male in the U.S. is, let's say, 5'10", And if standard deviation is, like 4 inches, one standard deviation is 4 inches. Okay, then one standard deviation above mean is there will be 5 foot 14 or 6 foot 2, right? And another standard deviation above that, one more, so 2 standard deviation above that, 6 foot 8, right? Think about it. Someone who is 6'8" tall is already, very tall. That's still, there is, 96, half of 96%. So you still have, like, um, 48%, probability of, especially if you're 6'8", that that will be, 96 minus 68 is what? 28, right? There is, 14% probability, right, between one standard deviation and 2 standard deviation, right? There's, 14% probability. And if you are somewhere between 6'2" and 6'8", I mean 6'6", 6'2", and 6'6", you're already falling into that 14% probability, right? And if you are somewhere between 5'10" and 6'2", you're in that 34% probability, right? Again, it applies the same, in the same way, downward, right? Well, suppose you're, 6'8", you are a very tall person, in the 2% upper tail, right? Okay. So it's an outlier. If you're like, 5 foot or less than, 5 foot, right? Below 5'2", right? And that's like 2 standard deviation, below 2 standard deviation. So you fall into 2%, bottom 2%. So that's clearly an outlier, right? But what do we do with the how does that we know already why normal distribution property is useful. We know that from Finance 100. First of all, mean variance ratio, being able to use mean variance ratio, right, is a very powerful tool in security analysis. I mean, also security pick selection of the securities in your portfolio. Also, you can nail the returns with probabilities. You can, in other words, you can add probability to your return forecast, right? But other than that, also it can be used very, it can come in very handy for value at risk. Value at risk. Now, generally they write value at risk like this. Okay, but this needs to be the reason they use lowercase a here is because it is to avoid confusion with variance, right? Because if you write the whole thing in uppercase, then it will look like this, and it can be confused, with variance. So that's why they write it with, lowercase a here. But I prefer to use, it's at, value at. Why don't you use, the symbol at, right? So value at risk is basically, a measure of downside risk and the worst loss that will be suffered with given probability, usually the bottom 5% or 5 percentile. Okay, now think about it. What was 5%, probability from our previous example? Severe recession, 5%. There's a 5% probability of severe recession, and if that happens, right, your portfolio return will be negative 37%, right? Now, although the expected return is 10% here, but, in the worst case scenario, what if the worst thing happens? How much will you lose? Negative 37% in this example, but in dollars, how much will it be? And what is the? It's not just that. Remember our standard deviation was, our standard deviation was our mean in that scenario, right? Our mean was 10%, right? And our standard deviation was, 18%, I believe, right? Wasn't it 18% in our example? Yeah, 18.63. So let's just round it to 18%. If it is 18%, one standard deviation. So that would be, I'm sorry, if one standard deviation is 18%, almost 19%. It's hard to. And this is going to be like 28%, isn't that right? Almost 30%. And then 18% below 10% would be almost, negative 8%, right? Negative 8%. I mean, it's rounded to 10%, right? Another 18%, right? Another 18%. We'll bring it to close to 50%. Yeah, true. But let's say that will be 46%. And another 18% will be 18, 20, negative 26%, right? So, now think about it. If the 5%, since the probability of falling below is negative 26%, or 26%, 30%, right? Negative. The probability of folding here is 2%, right? I mean, if there's a 5% probability of recession, so 5% area, lower tail 5%, right? 5% lower tail area. In other words, pretty much, it will be about this area, right? I think I better use right. You see what I'm talking about? If below 2 standard deviation, right? In other words, probability of earning anything below this, below 2 standard deviation, which is, negative 26%. If the probability of that area is 2%, right? You have to make a clear distinction between this percentage and this percentage. This percentage is return, right? These are the returns, right? Rate of return, right? And but this percentage is probability, right? They're not returns, but probability. Oh, it's so hard to. So now let's think about it. If the negative 5% probability area, right? Probability of, negative 5% will be this will be like 5% area. Of course, this is open-ended, right? It's not, I just circled it, but the lowest 5% area is open-ended, right? Open-ended this way, right? And then think about it. If the this is called Z-score. I mean, if 2% probability is 2% probability is starting from 2 standard deviations below mean, right? And 5%, bottom 5% probability area must start from, which is, start from before negative 2 standard deviation. And this point may be, so in other words, in terms of, standard deviation, right? This point may be negative about 1.7, 1.67 standard deviation, roughly, right? I guess negative 1.67 standard deviation, roughly. Okay, how about that? So, and expressing that probability in terms of standard deviation and from the mean, a standard deviation from the mean, is called Z-score or Z value, right? So think about it. Then we will know, right? What is the worst case scenario? Well, the probability of the worst case scenario is the bottom 5% or 5 percentile. And if that's the case, if we know what is the mean and standard deviation, then can we, so suppose our 10% mean return, and if our portfolio, total value of our portfolio is, let's say $10 million. If our total 10% return on 10 million is 1 million, right? And if our standard deviation is, roughly 20%, right? Our example was 18%, roughly 20% below 10% is negative 10%. So negative 10%, and negative 10% return means of $10 million, you lose 1 million, right? And the bottom 2% scenario, right? The worst case, worst of the worst, 2% bottom, worst of the worst, that would be negative 30%, right? With a $10 million portfolio, negative 30% means losing 3 million. But our bottom, then our worst case scenario is bottom 5%. So if we can find the Z-score of that point where bottom 5% starts, right? Which may be negative 1.67 standard deviation, right? And then if the standard deviation is 20%, right? 1.72 times 20%, our loss will be will be slightly less than slightly less than 30% loss, but we will know how much the bottom 5% case scenario loss will be. How much will be the loss in the bottom 5% case scenario? So that is what the value at risk measures, and we cannot do the due to time constraint, we cannot do the example, but in our next example, next video, we will do that example. Okay, so that's it for now. I will see you guys in the next video.